I'd like to cover cosine sine decomposition. It's one of the decomposition method, just like singular value decomposition, but it's a little bit different because, as you can see, if you have a matrix Q which is partitioned into Q1 and Q2, and when you conduct cosine sine decomposition, then the SVD of Q1 and SVD of Q2 is very much related. You have a matrix Q that is partitioned into Q1 and Q2. Matrix Q has column length of n, and Q1 has row length of m1 and Q2 has row length of m2. Both m1 and m2 is greater or equal to n. Cosine sine decomposition states that if the columns of Q are orthonormal, then you have orthogonal matrices of U1, which is a square matrix of M1 by M1, and U2, which is also an orthogonal matrix with M2 by the size of M2 by M2. And you have V1, orthogonal matrix V1, which has a size of n by n. And if you multiply what is written on the left side of the equation, you get the right side of the equation, which is partitioned into two parts. The upper part is consisted of, it's a diagonal matrix with cosines, cosine theta 1 through cosine theta n in all the diagonal places, and the bottom partitioned matrix is a diagonal matrix with sine theta 1 through sine theta n. So in order to prove this, I'm going to start with matrix Q. The columns of Q are orthonormal, so 2 norm of Q matrix equals to 1. And then the upper partition matrix Q1 the 2 norm of Q1 can be as big as 1, but depending on what you have in Q2, it could be less than 1. And then if you take the singular value decomposition of Q1, then you get U1 times sigma times V1 transpose. And move over U1 and V1 transpose to the left side, then you get U1 transpose times Q1 times V1 equals to C. We're going to call that C. We're going to assume that C equals to a diagonal matrix with cosine thetas in all the diagonal places. By assuming matrix C is a diagonal matrix with cosine theta 1 through cosine theta n, we're also going to assume that C1, so cosine theta 1 is that is C1, and cosine theta 2 is C2, and so on and so forth. We're going to say that C1 through some number CT is all equal to 1, and from CT plus 1 is less than or equal to 1, and all the way to Cn, which is greater or equal to 0. Then we can represent matrix C as this, because all the ones are identity matrix, and then all the leftovers are here as a sigma. Now so far we have Q1 matrix. Q1 matrix represented as, no, all the things that are on the left side is representing matrix C. So on the left side you have U1 transpose times Q1 times V1 equals to C. Now we need to incorporate Q2 into this. So we're going to say that Q2 times V1 equals to matrix W1 and W2. And the reason why we're doing this is because we want to match the dimension of what we have in here. Once we have Q2 times V1 equals to W1 and W2, we're going to multiply identity matrix that is the size of M2 on the left side and right side of the equation. But we're going to multiply on the left side. On the left side of both sides. So you have identity matrix size of M2 times Q2 times V1. That's equal to W1 and W2. The reason why we have this identity matrix is because we want this to be kind of like a placeholder. It shows, it acts like a placeholder. Maybe experienced mathematicians don't really need this, but I found this very helpful when I'm trying to integrate Q2 times V1 into the previous equation. And so by integrating this into the previous equation, which was U1 transpose times Q1 times V1 equals to C, that which is equals to identity matrix size of T, and then sigma, then we have this matrix on the bottom. So as you can see, U1 transpose Q1 times V1 equals to the identity matrix 0, 0, and sigma, which is what we had in the previous equation, and then we added this equation to the bottom of the previous equation, which then equals to which that turns this equation into identity matrix of M2, and this is 0 and 0, and transpose of identity matrix is the same, so it doesn't really matter by applying transpose or not. So we can kind of wrap this two together as one matrix, and then Q2 goes right below Q1, and then that is multiplied by V1, which gives us W1 and W2. So basically this part is added right below here, right below here. If you look at this matrix that I just combined together, it very much looks like singular value decomposition. So you have the Q matrix, and then you have the U matrix and the V matrix and the sigma matrix, or something that would represent sigma matrix if you were to relate this to singular value decomposition. So then you have this matrix, which has a partitioned, the first partition matrices of this matrix should have a 2 norm of 1. That's because this matrix that we have created, this is orthonormal matrix, and so 2 norm of each column has to be 1. So this part of matrix has to be 1. Then that makes since the 2 norm of identity matrix is always 1, so that makes W1 matrix to be 0. Now you have the right side of the matrix, or the right side of the equation, as depicted as here, and we were able to make W1 equal to 0, but W2 is non-zero, and it's also mutually orthogonal, because since sigma matrix here is not a identity matrix, all of these components are less than 1, and so sigma transpose sigma plus W2 transpose W they have to add up to become 1, so which is identity matrix. So each component of sigma squared plus each component of W2 squared at each column have to add up to become 1. I'm going to subtract sigma transpose sigma on both sides of the equation. This gives you W2 transpose W2 equals to identity matrix minus sigma transpose sigma equals diagonal of element S sub 1 all the way up to S sub n. And that we're going to call matrix S. If S sub k for k from 1 to n equals to square root of 1 minus c sub k, then from the chapter 2.6.3, distance between subspaces, from the textbook, it says z is going to be orthonormal when q equals to w transpose z, and when z equals to w2 times diagonal of 1 over s t plus 1 all the way up to 1 over sn. We have so far shows you that columns of Z matrix is orthonormal. Therefore, U2 transpose times Q2 times V1 equals to diagonal of S1 through Sn, which is matrix S. Since C sub k squared plus S sub k squared equals to 1, because of above properties that we showed of orthonormal columns, for k equals to 1 through n, they become the required cosines and sines that form matrix C and matrix S. And it concludes the proof. So I added some exercises after this, which kind of encompasses the proof that I showed you before, and I provided you with two matrices, or the lines of code that you can run in MATLAB, which will provide you Q1 and Q2 matrix, which you can plug it in, and if you can go through what I went through by proving this theorem, then you should be able to find the U1 matrix, U2 matrix, V1 matrix, and cosine and sine matrices. And once you have all those matrices, you can basically plug into all the equations that I have listed and solve all the questions pretty easily. They're pretty straightforward. Since this is a proof that I showed you today, I wanted to make sure that once you have the required matrices that composes U1 and U2, V1 and cosine and sine, that composes Q1 matrix and Q2 matrix. I just want you to see the relationship between one and another and how the singular value decomposition of Q1 and Q2 are very closely related. So that concludes my tutorial and all the exercises. And there are also hints that are provided right underneath the exercise. So I hope those are helpful. They were helpful to me when I was creating the MATLAB code myself. So hopefully you can find them helpful as well. Thank you.